Oh yeah, good. I like it. Sorry, let's see. Let me ask you this, just before we get into this problem. What's the difference between the limit existing at a point versus a function being continuous at a point? Is there a difference? Or are they the same?
There's a difference.
Which one's more restrictive? Which one requires more to be true?
The
functions.
The continuity requires more to be true, right? For the limit to exist, what does f of a have to be? Anything?
has to equal that.
No, come on. That's for continuity. See, that continuity says not only does the limit need to exist, but if that limit is L, then f of a better freaking be L. They better be the same. They better fill that sinkhole in, right? So continuity adds something. So this, if the limit exists at A, couldn't it look like that? In fact, it's got to look something like that, because what's the idea of a limit existing? It's approaching from both sides the same. It agrees on what's approaching. Does it have to actually get there? No. I like it. So you approach from this side, you approach from that side, and we just never get, oh shit, just forgot to finish reading. Oh shit. But if it's continuous, then we actually fill that hole. So that would be, continuity would say, not only does it approach the same thing, but it actually gets there. How are we doing there? So continuity is always harder to achieve than a limit existing. Limits don't care what actually happens at a point. They just get really close to it. Alright, how are we doing so far? Is that decent? God, I never want to play poker with most of you guys. No. Alright, so your question, which one was it again? Number 12?
Yeah.
Okay. So 12 gives you this big old mamma jamma piecewise function. I'm just trying to bring back mamma jamma. So it's that if x is less than 0. It's this if x is between 0 and pi. And it's that if x is greater than pi. And this one asks you, sketch the graph of the function and use it to determine the values of a for which the limit exists. So do you actually need the graph? Now you have to graph it for the homework problem. It says graph it. But to see if the limit exists somewhere, do you need to graph this? What are the points where it might not exist? Where the limit might not exist? Where might the limit not exist? Is this a continuous function?
Yes.
Yes, because sine is continuous and 1 is continuous, so their sum is continuous. Is this a continuous function?
Yes.
It is. Yes. They're all continuous. So they're going to be continuous wherever they are defined. Whatever their domain is, they are continuous there. So what are the only x values that might have a problem? Where they transition, right? So at 0 there might be a problem. In order for the limit to exist there, the limit of this as it approaches 0 better do what? In order for the limit to exist at 0, what has to happen? So at 0, whatever the function is on this side, better approach the same thing the function is on that side, right? And it's defined differently on both sides. Let me stop there for a second. Alright, so in this first one, is x allowed to equal 0?
No.
No. But what is the limit as x goes to 0 of 1 plus sine x? I like that.
One.
2.
Sine likes what? Sine likes
Sine likes y.
y. At 0 degrees, I have no y piece. So sine is going to be very sad. It's going to be 0. Sine loves it here, hates it there. Loves it here, hates it there. Sine is 1 here, 0 there. You with me? Cosine loves it there, hates it there. Alright. If only you were taught that way to begin with, calculus would be so much easier. But then they have this SOHCAHTOA bullshit just so they can make shirts. Camp SOHCAHTOA. Sorry. If you love SOHCAHTOA, great for you. You didn't need it. You just didn't know you didn't need it. In fact, it hurts you. So what this limit is 1, because the sine of 0 is 0. I like it. How are we doing so far? So from this direction is going to 1. Now I just got to see, and officially I should put a what here? You can do it. How it's the only way I can approach 0 for this? From below. Because on the other side, it's not defined to be this, is it? So what's the limit as x goes to 0 from above? What do I put in here? Above 0 is defined to be cosine x. And what is cosine of 0? 1.
Yeah.
I forgot what I just said. Sorry. So does the limit exist at 0? Does the limit exist at 0? Do the limits agree on both sides? Yes. So does the limit exist at 0? Yes, because what's it take for the limit to exist at a point? It just has to agree from both sides. We just saw it agrees from both sides, so the limit does exist. I like it. You guys with me? Now, it doesn't ask this question, but can somebody help me? Is it continuous at 1?
Yes.
Yes, it is, because it's an open circle for the sine part, and then the cosine part fills it in. So go through it. Is that a part of the question? No. Don't worry about it.
So is the limit the same as just like the value of f of x?
No. It isn't necessarily.
It's like a slope at that point, right?
Because the function could have no value at the point. We saw, like, for example, I really want you to understand, how do I say this? If this were allowed to, if it was this, then this function would be 1 at 0, would it? But since it's that, it would have an open circle at 1. How do I know it has an open circle at 1? Because it wants to be at 1. So if there's a place where it wants to be, then that is the limit. Does that make sense? That's actually kind of like what the limit is. It's where the function wants to be. It wants to go there, and it's like, I didn't make it. Right? That's an open circle. Because in pre-calculus, when you were graphing piecewise functions, which you should have done, I always teach my students, like if I wanted to graph this piecewise function, I would use less than 0 there, so I use like negative pi over 2, whatever. But I would put 0 in parentheses, so I know where the hell my open circle goes. There had to be a way that taught you how to see where your open circle goes. So you actually plug the function in and you see where it wants to be, and you put an open circle there. So now we're just kind of formalizing that. Okay, that was the limit of that function that you were doing. If you put an open circle somewhere, you were putting that was the limit you were showing. Does that kind of make sense? Because we have seen functions like this one. Remember this one? Right, at 5. And there is no function value at 5. That's the 5 doesn't exist. It doesn't agree. So the limit also doesn't exist. It doesn't agree on what it's kind of homing in on. It oscillates forever. Okay, maybe. So what about the other point? Not just do what we just did. Maybe I should leave something for you to do. I like that. Do what we just did for the other place where it could be a problem. And you'll quickly see that it is a problem.
Yeah.
All right, I'll let you guys see that yourself. Okay, any other questions from homework? Whew, we're losing time. It's okay though. Any other questions from homework? Or questions from this for you guys? All right. Okay, so let's step a little bit into the idea of 2-4. So just remind you guys, we went past 2-4. We've actually sort of gotten into 2-6. 2-6 is limits as x goes to infinity. So we talked about 2-6 a bit. Right? So now we're coming back to 2-4 just because 2-4 is a little freaky. 2-4 is your first little baby steps into rigorous proofs. And that just sounds exciting. Sounds like a trip to the dentist. Right? Rigorous proofs. Oh, good. So remember, recall, this is what we talked about with section 2-6. In order for the limit at infinity of a function to exist, let's say that this limit is 3. Then no matter what my function looks like over here, what has to happen eventually? If that limit really is 3.
It's got to be arbitrarily close to 3 after a certain point.
Good. So at some point, it better start getting really close to 3 or else the limit can't be 3, because that's the idea of limit. I've got to start getting close to 3, either like that, or I can even oscillate around as long as my oscillations get smaller and smaller and smaller. As long as there's some point after which I'm always closer than some number to 3. Right? And that some number was epsilon. If somebody says, I want you to be closer than 0.01, then I'm like, all right, I just got to here, and then I'm forever closer than 0.01 to 3. I'm forever closer than that. Then that would be the limit. Does that make sense?
Yes.
Let me try this again. So if you were here last time, I'm hoping that made sense. We had some nice stuff that was computer done, not hand done, because I know my hand done stuff is horrible. That looks like a duck monster. I don't know what that is. Just to make fun of myself. So if the limit really is 3, what does that fundamentally mean? That means after some point, like you said, after some point, and we call that point M, I'm going to be closer to 3 forever after that, however close you want me to be. So if you want me to be this close, there's some number after which I'm always closer to 3 than this. Come on now, really wrap your head around that. You're still looking at me like...
But right at M, it's as far.
Yeah, at M it could be that far away. But forever after M, I've got to be closer than this. I've got to be closer than that away. Right? Okay, maybe. If there's a point where it's not that close anymore, then I've just got to go further down. Maybe my M didn't go far enough down. But if I can't find any place where it's forever closer, then that can't be the limit. So we talked about the limit x goes to infinity of sine x. So why is there not a limit for that? What does it break here? If you think the limit 0, right? If you think the limit is 0, and I say, what would m be so that you're always within 0.01 of 0, can you do it? No, because you're like, look, I'm really close to 0, but then, here you're further than 0.1 away from 0. And it's going to take that shape forever, right? So there's an example of it in reverse. If the limit isn't that, then you can't ever make it so that it's always arbitrarily close to that. Okay, I like some of you guys' faces. You're like, yeah, you're making as much sense as I thought you would. Come on now. So you got to really think about what a limit should mean. What should a limit, if the limit really is 3, that means I should be able to get, at some point the function has to get really close to 3. So this is just a formalization of that. What does that mean? At some point, I should be arbitrarily close to 3 forever. I can never get further than that away. So if you want me to be even closer, I can find a place where it's always that close. Kind of with me?
Yes.
A little bit. A little tiny bit? Is that close? Okay. All right, sorry. Calculus. Oh, shit. Calculus humor, got all right, so where things will get freakier... This is the easy example. So where things get freakier is when you don't have infinity. It sounds like it shouldn't be that hard, but let's say I have a function. Let me just write this down. Limit as x goes to a of some function, I think it's L. So I'm not going to infinity. I'm just going to some finite number. Right? So just for simplicity's sake, I'm going to put this in the first quadrant over here. Put a there. L there. So whatever this function looks like, what could be at A? What could be there? So if this limit is L, what should it look like? Whatever it's doing, it can do any weird shit it wants to, but if this gets closer to A, then my outputs have to get smaller distance away from L, and my outputs have to get close to L. Right? But this idea of close is the idea that we have to formalize. What does close mean? So this epsilon was used for closeness when we went to infinity, right? The epsilon was how close they wanted me to be. Now I'm going to need 2 of those things, because not only do I have to be close here, I have to also be close there. Oh, yay.
Great.
Stay with me now. Or start to go with me, if you haven't. So let me just put in general, it could be an open circle there, couldn't it?
Yes.
Because I'm just talking about a limit here, right? It could be close, who cares? Whatever it does at A, who gives a shit? We're just talking about the limit. Okay, so if that really is the limit, let me make it a little bit easier just for this first time. Let's make it, if you're following along, I'm sorry. Too bad for you. I'm going to try to do one by hand, and then I'll pull one up on the computer to see what happens. What time we got? Not enough time for that. We'll just get the idea. So let me make one that looks like this. All right, sort of going through there. Okay. So it's not just a little more well-behaved function, right? So if somebody has to come along, given some epsilon greater than 0, and that's somebody going, well, if you think that's the limit, then I want you to be within 0.0001. All right, we're like, okay, and they don't have to sound like that, but that's just the image I have in my mind, right? They're the epsilon person. They give us, I want you to be this close, and you should be able to do that because you think it's the limit. So if I thought the limit was here, then I'm always going to be that far away, sort of. Do you see that? So if I got the right limit, I should be able to, so given this epsilon, that sets up this. They want me to be within epsilon away. So look, if you follow, I really want you to get this. So at the most, the output can be at most this far away. So like, oh shit, Jeff, I want to make this easier to see up here. Well, you'll never be able to do that. Right. Let me make this really close, all right? So there's my epsilon. That's how far away I want to be away from the limit. So if I go out, what does that mean? I can go that far away, input-wise, and I can go that far away, input-wise. So given an epsilon, can you find, given any epsilon greater than 0, can you find a neighborhood around, I love that word neighborhood, a neighborhood around A, where the outputs will always be that close? Now, at first you might not quite fully absorb this. That's fine. Nothing wrong with that. You never can fully absorb shit the first time you hear it, right? You got to let this slowly sink into your brain. Some of you guys look like you kind of get the idea. So if somebody else comes along and says, so that really is the limit. I don't care how close somebody wants me to be to it. I can always find a neighborhood that will end up being that close to it if it really is the limit. So given an epsilon greater than 0, we must find, let me just write down the result. A delta, oh snap. Might as well use a letter somewhere around epsilon. Might as well stay with Greek. Let's not go Klingon or something. All right, given an epsilon greater than 0, we can find a delta greater than 0 such that, oh boy, Jeff, proof language, I like it. If I am delta away from A, if I'm delta away, so this would be my delta. If I'm delta away from A, then I will end up being epsilon away from L. Well, I have more to symbolize what I said, yes.
So is epsilon specific to L?
No. It doesn't matter what L is. Epsilon is just how far away some other person wants me to get.
So from A or from L?
No. From L. Epsilon is all about... I see what you mean.
Okay,
all right.
so
Epsilon is all about the outputs.
Okay.
That's how far they want my outputs to be away.
And then delta?
Delta is all about the inputs. Okay. I love it. So deltas go with the X's. Epsilon go with the F of X, the outputs. I like it. I highly recommend that you read section 2.4. Try it. If you haven't read any of this book yet, give it a try. Just attempt it. Try it out. Or not. I'll never know. But you might as well see if this dude can write something, right? Look at this book. There's stuff, there's like words in there. It's got to be, because look at all the pages. So, at least read it. Try it. Next time I'm going to have a little handout. We haven't done an actual proof. We've just talked about the idea of it, right? So we have to do a proof, right? Oh, joy. And those of you who want to come in my class, some teachers don't even do this section. So you're like, let me see if I can jump there. And some of you guys will understand, it is bad to skip this section because this idea is used in a lot of other places in math. If you're going to do any more math at all, the more you understand this, the more you'll understand the idea behind other theorems and other higher math courses. Or if you're like, I don't want to understand, I just want somebody to tell me how to do this shit, I can't do much for you, so. Alright, but I'm always going to make sure you understand the idea behind something. Alright, that's enough. That's plenty for today.
Brain
So.
broken.
That would be great.
Go fix it. Maybe not get their quiz back? Alright. So you newbies, come with me. If you still want to be here.